Hello. In this lesson, we extend our statistics and probability unit, and we're actually going to start calculating some probabilities. So consider the following situation for our first example. Let's say Mr. and Mrs. Smith have two children. What's the probability that they had a boy, so first, and then they had a girl? So order is important here. Boy first, then girl, and then girl second. The first way you can determine this is just to list out all of the possibilities and find how many of them satisfy the condition that you were asked about. So that's going to be the longer way of doing it, but it's probably the most beginner-friendly way of doing it. So how many different two-child families can we have? Well, we could have a boy first and then a boy second. We could have a boy first and then a girl second. We could have a girl first and then a boy second. And then we could have had a girl first and then a girl second. So those are all of the two-child families that could have been had. How many of them had a boy first and then a girl second? Only one of them. So a 1 out of 4 or a 25% chance. That's option number one, is you list out, we call this the sample space. We list out all of the possibilities, and when we identify all of those successes. Option number two is to calculate it using mathematics instead of just listing them all out. So probability of boy first and then girl second. We would take the probability of having a boy first and then the word and, this is kind of key, in probability implies multiplication. Boy first and girl second. What's the likelihood that there was a boy first? Well, a 50% chance. Times, what's the likelihood that a girl is second? Well, also another 50% chance. 1/2 times 1/2 is 1/4. 25%. It works. Here's another reason why it has to be multiplication. Let's say some people sometimes think that maybe it's addition. Watch what would happen if you thought this was addition. If you said, what's the likelihood they have a boy first and then a girl second, and you used addition as the operation in between, 1/2 times 1/2 would be 1. You would say it's a guarantee that they have a boy first and then a girl second, which is not the case because there are other possibilities. It's not a guarantee that they have a boy first and then a girl second. So that's why it's not addition. In probability, if it says the word and, it is multiplication. The reason that this process works is because these compound events meaning more than one, these multiple events are said to be what we call mathematics independent. And we're going to define these terms on the following page. So a compound event is an event that is made up of two or more simpler events. Our last one was a compound event because, as we saw, it was made up of two simpler events, boy first and then girl second. The joint probability is the corresponding probability of compound events. Two events are said to be independent if the two events, so independent events are two events are independent when the outcome of one has no effect on the other. You might think about the word independent and think of free, like freedom, and that's true. One is not going to affect the other. They are not connected to one another. One is free from the other. The opposite of that would be if the two events are dependent. So two events are dependent if the outcome of one has an effect on the other. If you need to pause the video now to fill in the definitions, go ahead and do so. Otherwise, I'm going to scroll down. Probability of independent events. If two events are independent, then the probability that A occurs first and then B occurs second is you take the probability of A and then you multiply it by the probability of B. As I said, and in probability means multiply. That's if the events are independent. If the events are dependent, the probability of A first and B second is obviously the probability of A first, and then I multiply by the probability of B given the fact that I already know that A has occurred following A. And this might change, or this will change based on the fact that A has occurred. So we'll see just in different scenarios. So the first one, you can see it's just the probability of B. B doesn't care that A has already occurred. In the second one, because if the events are dependent, if they rely on one another, the probability of B is going to be different than the probability of B occurring after A has already occurred. Maybe there's less options available, as we'll see. So let's try some examples. State whether each is independent or dependent, and then calculate the probability. Let's say I roll 2 dice. What's the likelihood that I roll a 6 on the first one and then an odd number on the second? So probability of a 6 and an odd. These two events are independent. What happens with one dice is not going to affect the other. So your determination of independent and dependent is going to be based on just experience and kind of common sense. So there's no other way to really do that right now that we know of. Just you have to know that one dice is not going to affect the outcome of the other. So I want the probability of the first one being a 6, and then I multiply it by the probability of the second one being an odd. What's the likelihood that the first one is a 6? Well, a dice has 6 sides, and only one of them is a 6, so a 1 out of 6 chance. And then the probability that the second one's an odd. There are 3 numbers that are odd, 1, 3, and 5, so a 3 out of 6 chance. How do I multiply fractions? Straight across. 1 times 3 is 3 out of 36. That is a 1/12. If you do it as a percent, it's 0.083. So 8% chance that the first one's a 6 and the second dice is going to be an odd. Second scenario. Let's say you draw 3 cards from a deck without replacing them, and that's key here. That's going to determine which type of situation we're dealing with. Find the probability of getting the cards in the following order. We get a diamond first, and then a club second, and then a not club third. Well, first off, these are going to be dependent events. What happened before dependent is going to change the likelihood of the second and third things occurring because there's less cards in the deck. If I were to draw it out, this is what it looks like. I would like the probability that the first card is a diamond, and then the second card is a club. That's a symbol for clubs. It looks like a clover. Excuse my art. Following the first one being a diamond. And then the last one is not a club, following a club on the second one and a diamond on the first. If you haven't played with cards before, maybe might be wise to kind of fresh up. Let's actually use Google. So let's say deck of cards. If I just will show all the possibilities. Yeah, okay, good. Maybe this picture right here. Too much zoom in. There we go. That probably should be good. If you've never looked at cards before, then here's a little summary. There are 52 cards in the deck. There are 52 cards because there are 4 suits. Here's the spades, hearts, diamonds, and clubs. So there's 2 types of black cards and 2 types of red cards. Within each suit is what we call these. So spades, hearts, diamonds, and clubs are all suits. Within each suit, there are 13, what we call these ranks, 13 different types of cards. 13 times 4 is 52. So there's the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then there's the jack, queen, and king. And there's 13 of each of those. So 13 hearts, 13 clubs, 13 diamonds, 13 spades. If you need to, grab a deck, kind of look around. So here we go. First one, what's the probability that the first card is a diamond? We said that there are 13 diamonds and there are 52 cards in the deck. And now I want a club. There are 13 clubs still left in the deck, but now there's not 52 cards left in the deck because I did not replace. I didn't put that diamond back in. There's only 51 left remaining times. Now I want not a club. How many not clubs are left in the deck? Well, originally there are 39 not clubs. That's these right here. There are 39 not clubs to start off in the deck, but I already picked one of them, that diamond. There's only 38 not clubs left in the deck, and there's only 50 cards left to choose from because I've already selected 2. And that's why you can see these probabilities change based on what happened prior. And then I just multiply straight across. So 13 times 13 times 38. The top is 6, 4, 2, 2. The bottom 52 times 51 times 50 is 132, 600. So then I divide those two. And the likelihood of that occurring, assuming I typed everything in correctly, is about a 5% chance. 0.048. For this section, it's probably wise to go out maybe 3 decimal places will be consistent. So that's 4.8% likelihood of that occurring. Gonna have you try the following situations. That zoomed out too far. That's probably good. So you try the following situations. Let's say first one, a search and rescue team believes there's a 40% chance a plane went down in that following area. What's the probability it went down in the area and also landed in the water? The second one is state whether this is independent or dependent, then calculate the probability. You flip a coin 3 times, the likelihood of getting tails 3 times in a row. Pause the video now, unpause it once you've had a chance to try. Okay, here we go. The first one is, this is dependent because the likelihood of landing in water depends on the fact that you landed in this area. So this is the probability that you went down in the area and also went in the water. So this would be the probability that you went in the area and multiply by the probability that you went into the water for that area. And they told you the probability of going down in that area is 40%, so this would be 0.4 times what's the likelihood of going down. So once you're in this area, there's a 25% chance, because a quarter of that area is water, so 40% times 25% turns out to be 10%. The last one is independent. What happens with one coin flip is not going to affect another coin flip, and there's a 50% chance for tails on each one, so 0.5 times 0.5 times 0.5 turns out to be about a 12.5% chance that you're going to get tails 3 times in a row. So there you go, there's the first section. The second section deals with whether 2 events can even occur at the same time. Mutually exclusive events are 2 events that cannot occur at the same time. They have no overlap. It's impossible for them to occur at the same time. We use these types of events when we're considering whether event A or B might occur. So if 2 events are mutually exclusive, if you made a Venn diagram for them, there's no overlap. They cannot occur at the same time. The probability that A occurs or B occurs is simply the addition of the 2. And you'll see the word or in mathematics is associated with and. If they use the word or sorry, not and, associated with adding, the operation add. If they use the word or, you're going to be adding the 2 probabilities. That's different than before, where if they use the word and, that meant multiply. So and means multiply in probability, or means add. Yeah. Example. Let's say that you're playing Monopoly. Just to make it kind of an easier situation, let's just assume 1 die for right now. You could make it more advanced and do 2, but let's just do 1 die for this situation. Let's say you're currently on Park Place. What's the probability that you land on or pass go? That would be the probability of getting at least a 3. What's the probability of getting at least a 3? Well, that's the probability of getting a 3 or a 4 or a 5 or a 6. What's the probability of getting a 3? 1 out of 6. What's the probability of getting a 4? 1 out of 6. Probability of getting a 5? 1 out of 6. Probability of getting a 6? 1 out of 6. So there's a 4 out of 6 chance of getting on go or passed, because you could get the numbers 3, 4, 5, or 6. So what is that? 2/3 or 66.6, repeating, 67% chance. Second one. Let's say you're on Community Chest. What's the probability you land on free parking or chance? That's a probability of a 3 or 5. So probability of 3 plus the probability of 5. 1 out of 6 plus 1 out of 6 chance. So a 2 out of 6 chance, which would be a 33% likelihood. What if I asked you to find the probability of drawing a card from a deck and asking you the probability of drawing a 2 or a diamond? We'll come back to this question here in a second. Let's just try doing it how we did before. We want the probability of getting a 2 or a diamond. And you might be tempted to say, oh, okay, it's or. I mean, I just add probability of 2. Or means add probability of getting a diamond. And you would say, okay, so probability of 2, what? There's 4 2s in the deck, because 2 heart, 2 club, 2 diamond, 2 spades, so 4 out of 52. Plus, there are 13 diamonds in the deck, so 13 out of 52. And you'd say, oh, it's 17 out of 52 for sure, because I just added 2. But let's draw the picture and actually see. How many cards in the deck are a 2 or a diamond? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's only 16. So why is it that if I draw the picture, it says 16 out of 52, but when I add the 2, I get 17 out of 52. And the reason is because of this overlap. These 2 events are not mutually exclusive. Since they are not mutually exclusive, we need to subtract off their overlap. That 2 of diamonds got counted twice. It got counted once as a 2 and once as a diamond. So I need to alter my calculation. If there is overlap, I need to subtract off the overlap because it got counted twice. I need to subtract off the probability of being a 2 and being a diamond. The 2 of diamonds got counted twice. And when I subtract it off, then I will get the correct answer. So if there is overlap, you need to subtract off that overlap because it got counted twice. If I use highlighter, you'll see I count these, so I count all 4 of those, and then I go and count all 13 of those, but this 2 just got highlighted twice, so I need to subtract it off once. So that's the formula that we use if 2 events are not mutually exclusive. They are not mutually exclusive if they overlap. They are not separated. They can occur at the same time. And because they can occur at the same time, I need to subtract off the likelihood of them occurring at the same time because it got counted twice. It got counted once for A's probability and once for B's. So if 2 events have overlap, you need to subtract off their overlap because it got counted twice. That's the probability formula for not mutually exclusive events. Examples. Let's say you're going to draw a single card from a deck, state whether each is mutually exclusive or not, and then calculate. What's the probability of a 7 or a jack? Well, first off, can I draw a single card out of the deck that is a 7 and a jack? I cannot. So these are mutually exclusive. There is no overlap, so I don't need to subtract anything off. This is simply the probability of a 7 plus the probability of a jack. The probability of getting a 7 is 4 out of 52. The probability of a jack is 4 out of 52. If I add those together, that's an 8 out of 52 chance. And 8 out of 52 as a decimal, it's about 15%. 0.154. Second scenario, what's the likelihood I draw a single card out of a deck that's a spade or a 9? First thing I need to ask myself is, are there spades that are 9s? And yes, there is. There's one card that is. So this is not mutually exclusive. Those 2 can overlap. They have something in common. So this is going to have to subtract something off. The probability of a spade. Or means add the probability of a 9. And I need to subtract off the spade and 9, the 9 of spades. The probability of being a spade, there's 13 out of 52. Probability of being a 9, there's 4 cards in the deck, and there's 1 card, that's a 9 of spades, and we did this one earlier. All of these ones turn out to be the same type of calculation. 16 out of 52, just recalling from before, was our 0.308, 30.8% chance. Gonna have you try, and then that'll be it. So here's what we call a two-way table. You're collecting data from a blood bank concerning their donors from the past 5 days. State whether each is mutually exclusive or not, and then find the corresponding probabilities. So let's just practice reading the table before I set you off. So let's say I look at this. This 65 tells me that there are 65 people that have Rh negative blood, because that's the total for that row. If I look at this 45, that means there are 45 people that were sampled that have type B blood. If I look at this right here, that 8, that means there are 8 people that have type B and are Rh negative in terms of their blood. So that has type and then their Rh characteristic. The last number, this bottom right, is the total for all. There were 409 people that donated at this blood bank. So that's how you read the table. Can you find the following probabilities? Pause the video now for maybe 2 minutes. Unpause it once everyone's had a chance to try. Okay, let's do the first one. Probability of type A or B. This is what I would do. I would use colors or just highlight some things. So here's type A blood. Here's type B blood. Do they overlap at all? They do not. So these are mutually exclusive events. They are not going to have any overlap. I don't need to subtract anything off. This is probability of type A blood, or, so I add probability of B blood. What's the likelihood of having type A blood? 164 out of 409. Type B blood is 45 out of 409. And 164 plus 45 is 209, so 209 out of 409. And if I divide those two to get it as a percentage, it's about 51%, 0.511. So about 51% chance someone has A or B blood. Okay, let's erase this now for the second scenario. Second scenario, what's the probability someone has type O blood or is Rh positive? So again, let's use some colors. Let's use purple this time for O, so type O blood. Or Rh positive, this one they do have overlap, so these are not mutually exclusive. I'm going to have to subtract off the overlap because this 156 is going to get counted twice. The probability of O plus the probability of Rh positive minus the probability of O and Rh positive. Likelihood somebody's type O, there's 184 out of 409, so 184 out of 409 plus Rh positive, there's 344 out of 409. If you add those together, you're going to see that's bigger than 409, so you have to subtract something off. You need to subtract off 156 out of 409. And when you run the whole entire calculation, you're going to get 372 out of 409. That's like 91%. Looks like I did something wrong on A. Let's go back and look. Type A or B, 164.45. Yeah, don't look at that. That's incorrect. What we did up above was right. I think that was type A or AB blood. That is. So this, I must have had a different question in the past where it was A or B blood. So this is correct, 51%. This bottom one of 184 plus 344 minus 156. Yep, that all looks good. So 91% for this one and 51% for the second one. And that's it. Thank you very much. Have a good day.